We want to go straight to question number 7 on our worksheet that we had for homework last night, which says the pilot of an airplane wants to go directly south at 130 meters per second. However, there's a wind blowing to the west at 20 meters per second. With what velocity, including the direction, does the pilot need to aim the airplane? We're going to the south, or at least we want to go to the south. We'll assume that the pilot is good enough to actually go where the pilot wants to go. So let's assume that we go to the south. Is that a solid line vector or a dotted line vector? When we go in a particular direction, it is good. It's dotted line vector. That's not contributing to where we go. It is where we go. Things like wind contribute to where we go. Okay, this is where we go. So we're going to make that a dotted line vector. I'm going to draw it to the south at 130 meters per second. We have another one. That's the wind blowing to the west at 20 meters per second. It's going to look something like this. Solid line vector, right? Because it contributes to where we go. How do I put those two together? How do I put those together, Cody? Front to front. Yeah, that's the easiest way to do it, is front to front. Didn't we say that vectors always go front to back? Yeah, go ahead. Yeah, we're talking about the solid lines. They're always front to back. In other words, the contributing vectors, sometimes we call them, they go front to back. But when we're talking about that resultant vector, it has to go from start to finish. And the only way that dotted line vector, that resultant vector, can go from start to finish is if we're front to front or back to back with it. So you got two options, really. You could draw it right here, or you could draw it right here. But I suggested yesterday that we always just draw it at front to front. Draw it at the end. So there's my 20 meters per second. It's to the west. My other vector, my third vector, will go this way, front to back. This is what we want to find, right? Now, we're finding the hypotenuse, which is what we've been finding on all of these problems, but the hypotenuse is not the resultant vector this time. Mathematically, that doesn't make any difference, but conceptually, what we're solving for, it does make a bit of a difference, right? It's not the dotted line. It's not the result. We're looking for the angle here as well, and the angle is always measured from the very start of the diagram, right? Start, back to back. All right, let's find the value of V. 130 squared plus 20 squared. Let's square root that. Let's find the value of theta, the inverse tan function of opposite over adjacent. Do the math here. V works out to be 1.3 times 10 to the 2. 2 significant digits, right? So the speed of the airplane doesn't increase dramatically. It does a little bit, because to 3 significant figures, it would be a little bit more than this. But the wind basically doesn't cause it to speed up very much. But it does cause it to go off course. The inverse tan of 20 over 130 is 8.7 degrees. So listen, if we have a wind that's to the west, a wind that's to the west, where do we have to aim in order to go straight south? We have to aim to the east, right? We have to aim opposite to the way the wind is blowing. So going to the west, we have to aim to the east. Now, how do we express that 8.7 degrees? 8.7 what of what? Well, we know that this vector here is going south and east, right? Okay, we know that it's not going north, because it would be going up that way if it was going north. South and east. So it's a matter of which one comes first. Is it south of east, or is it east of south? You're always going to measure the angle from either this axis, this axis, this axis, or this axis. You could say here, I'm measuring it from the south axis, right? You could say I'm also measuring it from this line right here. Pay attention to the axis. Pay attention to the north, south, east, west. I'm measuring it from the south. From the south. From south. Now, which way do I go from south? East. I go east from south. So I'm going south, then I'm going east. East from south, or east after south. I would say it's east of south. Does that make some more sense? Yep. Yeah, we can. Yep. Question 6 says, the captain of a ship wants to go directly south across the river at 15 meters per second, but there's a current in the river that's 5 meters per second to the east. What's the velocity, including the direction that the captain has to aim? Once again, this is where we want to go. We'll assume that this is where the captain actually goes. We're going to make that a dotted line vector, because it's not contributing to where we're going. It's where we're going. There's a river current of 5 meters per second to the east. That's to the right. I'm going to draw that so that it's drawn front to front, so that my third vector, my solid line vector that contributes to where I go, this is where I'm aiming, is going to be drawn from front to back here. So let's solve for V here. Let's erase that 15 actually and plug it in over here so a little bit more clear. Okay, solving for V, it's not the, sorry, it is the hypotenuse. It's not the resultant vector. That's okay. V ends up being equal to the square root of 15 squared plus 8 squared. And the value works out to be 16 meters per second. Theta, as measured at the beginning, at the start of the diagram, is the inverse tan function of 5 over 15. Works out to be 18 degrees. Now, 18 degrees south and west, right? South of west or west of south. Where are we measuring it from? Are we measuring it from the south axis or are we measuring it from the west axis? Ethan? Which way are we measuring it? From the south or from the west? Right. So it's going to be something of south or west of south. 18 degrees west of south. Oliver, is that okay? Yeah. We good there? All right, I told you that the quiz that you're going to have on Monday is going to be either like question 6, question 7, or like question 5. I want to give you one more example of a question like number 5 to work in at your desks for a couple minutes, and then we will go over that in class, and then we'll move on and assume that you're going to be good for the quiz on Monday. We'll find out, I guess, on Monday. Here's the question. Okay, let's have a look at this question now. It says a boat heads west across the 2-kilometer wide river at 7 meters per second. The current in the river is 3.0 meters per second to the south. We want to know the velocity of the boat relative to the shore, how long it takes to cross the river, and we also want to know how far downstream the boat ends up on the other side. Okay, question like number 5 on our worksheet here. Boat heads west across the river. If it heads west across the river, then that means it's aiming. That means that it contributes to where we actually go. So we're going to make that a solid line vector. Let's say 2 kilometers per hour. Sorry, no, not 2 kilometers per hour. It's going to be 7 meters per second. We also have a current that's going 3 meters per second to the south. So we're going to draw that to the south right here. 3 meters per second. Both solid line vectors because both of those contribute to where I go. Now, the river would look something like this, and we can draw in the width of the river as 2 kilometers. Just remember that the width of the river can never go in the same vector diagram as your velocity. If you've got a vector diagram with velocity, it has to be just velocity. The 2 kilometers is important, but that's going to be a separate diagram. Now my resultant, my dotted line vector, where I actually end up going, the answer to question A is going to be that dotted line that joins the start to the finish. This is R, this is theta. R is equal to the square root of 3 squared plus 7 squared. And theta is equal to the inverse tan function of 3 over 7. Who's got the value of R there? 7.6 meters per second, thank you. And what's the value of theta? Go ahead.
23 degrees.
We're going to make it 23 degrees, and it will be south of west because we're measuring that angle from the west axis, and it's south from the west or south of west. Had you drawn it the other way around, 3 then the 7, then you would have gotten an angle of about 67 degrees west of south. That would be equally as correct. It's the time that it takes to cross the river. The time that it takes to cross the river. Well, for that, we're going to say V is equal to delta D over delta T, and rearrange it to solve for T. This boat is going at a constant speed across the river, constant velocity across the river, so we're going to use our group A equation. V is equal to D over T. What's the displacement? 7.6 meters, sorry, 2.0 kilometers. It's the only displacement we have. What's the velocity we use? This is the tough one. What do we use? Is it 7.6, 3, or 7? Yep, it's 7. We use the velocity that's in the same direction as the, oh, wait a sec. We use the same velocity that's in the same direction as the displacement, but what do we got to do here? I missed something. Yep. Good. Let's change the, or we could change the meters per second to kilometers per hour, but easier to do what you suggested. 2,000 meters over 7 meters per second. And that should equal 286. Let's go with the unrouted number though. 285.714. Which we round that to 2 digits, it would be 2.9 times 10 to the 2 seconds. All right, there you go. There's the time. Now, how far downstream does the boat end up? Once again, constant velocity, displacement over time. But this time, we're looking at the component of the velocity in another dimension, another direction here. The velocity this time will be, since we're looking for how far downstream, the velocity will be 3 meters per second times a time of 285.714. Can anybody tell me why I'm allowed to use that time for both velocities? X displacement goes with X velocity. Thank you. Y displacement goes with Y velocity. Time can go with either one. How come? Because it's scalar. Good. So we got 3 times that time that we found for the other component. 857 or 8.6 times 10 to the 2 meters. Good. If you're really comfortable with question number 5 or this question, which is just like question number 5, question number 6 and question number 7, then Monday's quiz should be a breeze for you. Okay, no tricks to it. Okay, other than what you've already seen on these questions, you should be in good shape.